Okay, I'm going to talk about the Cauchy Schwartz inequality. Sometimes just called the Cauchy or Cauchy's inequality. I'm going to talk about it and prove it and muck around with it in this and subsequent screencasts. Given A1, A2, given A1, A2, A3 up to AN, and B1, B2, B3 up to Bn, two sequences of any numbers, any real numbers, then Cauchy's inequality states the following. It says that A1 squared plus A2 squared plus AN squared times B1 squared plus B2 squared plus plus Bn squared is greater than or equal to A1 B1 plus A2 B2 plus plus AN Bn all squared. Just pinching a little bit. So there it is, and it looks rather abstract in its own peculiar way. I can rephrase it in a couple of ways. I can say sigma from I equals 1 to n of AI squared times sigma from I equals 1 to n of BI squared is greater than or equal to sigma AI BI, and this is I equals 1 to n again, all squared. So it's just the same way of saying another thing, or when I'm thinking about it, I'll just go sigma A squared, sigma B squared greater than or equal to sigma AB squared. They're just different ways of saying the same thing. So I'm just going to give you an example with numbers in it. Just to show you how it works. I'm going to say A is the sequence 1, 2, let's say 4, and B is the sequence, let's say 2, 2, 3. Let's say that. And so Cauchy's inequality says sigma A squared, sigma B squared greater than or equal to sigma AB all squared. So that says that, let's put some brackets in them, 1 squared plus 2 squared plus 4 squared, I'm just evaluating this term here with A, times 2 squared plus 2 squared plus 3 squared, I assert is greater than or equal to sigma AB squared. So it's 1 times 2 plus the next one 2 times 2 plus the next one 4 times 3 all squared. Okay, so what's the left hand side? Well, that's 1 plus 4 plus 16 times 4 plus 4 plus 9 equals 21 times 17. Oops, 17. 21 17s, 7 1 4 2 1 7 5 357. What's the right hand side? From up here, 2 plus 4 plus 12 squared equals 18 squared, which is 4 down 6 to carry 12, 1, 8, 4, 0, 304. So this is asserting, well, it's giving us the information that 357, which is the left hand side, is greater than or equal to 304, which it is. Of course, that's not a proof. That's far short of being a proof, but it's just showing us that it does seem to work. So let's have a look at a proof of this statement. Well, what I'm going to do is I'm going to consider, and this is kind of a shorthand. The word consider in mathematical proof means I'm just going to pull this thing out of thin air and play with it, and it'll end up showing us what we want to show. So consider this. It's going to be the sum from I equals 1 to n sum from j equals 1 to n of ai bj minus aj bi all squared. And I'm going to call that q. And of course, q is greater than or equal to 0 because it's the sum of squares. Q equals the sum of at least non-negative things. Because it's a whole bunch of stuff squared. Okay, so let me just think about this, and I want to evaluate it. See, it's a rather peculiar thing, and it's the sum. This number in here that we're squaring might be positive or might be negative. We don't know very much about it, but what we do know is that when we square it, it's positive, and we're adding together lots of positive things, or at least non-negative things. So it's sigma over I and j of, well, let's just multiply this one out. ai squared bj squared plus aj squared bi squared minus 2 ai bj aj bi. These two come from the cross terms when I'm evaluating this square here. Well, let's just have a look at that. So, well, let's just have a look at this. Let's just have a look at this one here. Let's just have a look at that. So we need sum over I, sum over j of ai squared bj squared. And I'm being somewhat slipshod in my notation because what I really should do is put brackets around there. And then considering the bracket is sigma over I of something, we're summing over j, and this guy here, that is a constant. So I can take it outside the summation. And then I can look at this term here, this summation here. As far as the summation over I is concerned, this guy's a constant, and so he comes out of the summation. All I'm doing really is saying sigma for I equals 1 to n of, let's say, 3 times some function of I, and that equals 3 sigma f of I equals 1 to n. All I'm doing is observing that that's a constant because it doesn't change with I, you see, it's just a number. And in the same way, this which way around, this guy here is just a constant as far as the j is concerned. And now we're using the same trick again, which is a recurring theme in Cauchy's inequality. We're using the same trick again to pull this guy out of the summation. So that equals sigma over j bj squared times sigma over I ai squared equals sigma a squared sigma b squared. Okay, and of course the same line of logic applies to this guy here. So let's just have a look at this. And what have we got here? This is q again, isn't it? So q equals 2 sigma a squared sigma b squared, because we've got two terms that are the same, minus 2 sigma over I sigma over j, the 2 has come out, ai bi aj bj. You see, all I'm doing is rewriting these terms in a slightly different order and then bracketing it to make it work for me. Equals 2 sigma a squared sigma b squared minus 2, and it's the same line of logic again, taking out the i's and taking out the j's, sigma, I may as well write it in full, I equals 1 to n of ai bi all squared, just by the same line of logic. And we know that this is greater than or equal to 0 because q itself, here it is the sum of squares. So we can cancel out by 2 and observe that, no, we can cancel out the 2, that sigma a squared sigma b squared minus sigma a b all squared is greater than or equal to 0, or sigma a squared sigma b squared greater than or equal to sigma a b all squared, QED. Okay, this is Cauchy's inequality, Cauchy. And I quite often say this is my desert island inequality. If I just had to choose one inequality to use, if I, for some reason, I had to pick one inequality, this is the one I would choose. It's more important than any other one because it's got applications in physics, it's got applications in thermodynamics, it's got applications in information theory and coding. It crops up all over the place in a way that the other inequalities that we'll deal with in this course don't. So I'm just going to stop there and leave Cauchy's inequality. I want you to observe how, when I'm thinking about it, I'll write it out again and again and again, just to stick it in my mind. And we'll talk about applications and examples and so forth in subsequent screencasts, but I'm just going to stop there. Okay?